Okay, this is question 54. It says a stone is dropped into a river from a bridge 43.9 meters above the water. Another stone is thrown vertically down 1 second after the first is dropped. The stones strike the water at the same time. What is the initial speed of the second stone? So basically you have two people dropping rocks. Draw it something like this. Person one, person two. The first person just simply holds the rock, lets it go, and it falls. So the second person takes it and throws it down. So there is a force added to the second one, right? This is why they're able to reach the water at the same time. So you have some, I think it's in water, whatever. So this one's thrown. This one just drops. And then this is 43.9 meters. Okay. So initially I would do the same thing. I would write for number one, which is person number one over here. You have this information. You have initial velocity. This actually equals 0 because you're just simply holding it. It starts at 0 and you let it go. So you also have acceleration, which is your negative 9.8 meters per second squared. And then you have the height, or when you go to use the physics equations, when you have the equation that has x, you can change it to y. So in this case, we're just going to say y. Y equals 43.9 meters. And then we don't have the time. The time is what we're looking for, right? Because that's what it was asking for. So when we find the time that this one falls, we know this must hit the water at the same time. So if we take what they said, and this person waited exactly 1 second and then threw it. So if we find this time, we can add +1 to it, and then we'll have the time for this. And then we can go backwards and find the initial velocity. So we have the initial info, right? So we can go down and we want to find the time. So let's go back to our equation we used before, where you have this time I'm going to use y instead of x. Y final equals y initial plus v naught times t plus 1/2 at squared. So we have the y initial is 0 because it starts at 0, it goes down to 43.9. So we have y, this is basically y final. You have 43.9 meters, and that equals an initial velocity of 0. So this whole point right here gets wiped out. This is 0. And then we have 1/2 at squared. So you have 1/2, and then you have a negative 9.8, and then you have t squared. So now all you have to do is solve for t. So you have t equals 2 times 43.9. I'll put a little parentheses in there just to make sure you know those are separate. And then this is divided by 9.8. And then of course this was squared, so we square root the other side. So that's the thing you want right there. So after doing this on the calculator, you should have 2.99 seconds. Okay, so this is time 1. Come on. And then, as I said before, running out of places in my book here. If we look at time 2, this is just +1 because it initially said +1 to the first one, so it should be 3.99 seconds. Now that we have this information, we'll draw a little line here to separate this. So now again, let's make the same chart with number 2. So number 2, again, initial velocity is what we're looking for, right? It wants to know what it is. Acceleration is then still negative 9.8. And in this case, because this is a time, we don't need the negative, so I actually just kind of lost it back here. It should be 2.99 seconds. So don't worry about the negative in this case. That's why I was saying you can add it, and then it'll just kind of come out in the wash when you get to the end. If it doesn't make sense, then you didn't need the negative sign. So we're not going to need it here either, probably, unless I make this time negative. So I'll just leave it positive. 9.8 meters per second squared. The fall height is then the same. Y final equals 43.9 meters. And then we have the time, which is 3.99. So if we go back and we use this equation again, we have, let's do this, try to save as much space as possible. 43.9 meters equals, y initial is still 0. Now you have v naught, which is what we're looking for. V naught times t, which is 3.99 seconds. And then we have plus 1/2 9.8 meters per second squared. Sorry, my handwriting's getting kind of small because I'm running out of room. And then this time squared, so 3.99 seconds squared. So hopefully you can see that. That is squared on there. Probably just scoot that over a little bit. So that's squared. So then we put this into the calculator. Again, so we do all the algebra. We rearrange this to equal v naught, and then you just put it in the calculator, and then your initial velocity should be then it's again the negatives, but you're going to get 12.3 meters per second, if I can do that correctly. Okay, so you have this information here. I'm going to remove some of this to make, so again, technically the initial velocity, if you choose the coordinate system, this is most likely going to be negative, just from the reference point of where it's starting. And then if we try to plot this, it's going to be in a negative direction. So if we just make something like 1.0 for time, so I'm going to make this time in seconds, and then we have our 2.99. Then you have your velocity up here, maybe we'll write down here, velocity meters per second, 0 point. And then we know it goes to negative 12.3, so I'll write this down here, negative 12.3 meters per second. Okay, so we do the first rock that was dropped. It started from an initial velocity of 0, and then went down for 2.99 seconds. So it comes down, and again, this is not on graph paper or anything, but comes down and then stops. So then the second rock is then delayed. I'll draw this down here. It's delayed by 1 second, so we have this delay. So it starts right here. And we know the initial velocity is this 12.3 meters per second. And then it continues along the same path and stops at the same time. So we didn't actually solve for the final velocity of this, so we don't know what it is, but this is the graph that would go for it. So hopefully that makes sense.